So thank you very much for this opportunity. I want to thank the principal and all the organizers for having invited me here. Before I even start saying anything about quantum, I seriously want to congratulate all the students who were involved in producing this Reverberations 26 magazine. I'm told that a lot of undergraduate students were involved in this. I think it certainly deserves a very nice round of applause. Can I I'll get to this now. The title is Quantum Concepts. So the way I have arranged this is, Professor Natarajan has already given you all the information. So I will continue as long as there is some reasonable time. I will stop at any point you want. I will take questions. If you interrupt me now and then, or if you want to ask at the end. நீங்க கேட்குற கேள்வி இங்கிலீஷ்ல கேட்கலாம் இல்லை தமிழ்ல கேட்கலாம். I can take both languages. Pointer. So this is quantum concepts. Quantum concepts because, as Professor Natarajan told you, and as many of you know, many concepts in quantum physics are very different from concepts in classical physics. So in the concepts we have to learn. Next slide. So there are many challenges in quantum physics. There are very new and abstract concepts. The concepts challenge our common sense. It seems to rely a lot on mathematical equations. Experiments are not that easy to perform. This was the state of affairs. Now in the black club, whatever I have put on here, this was the state of affairs till, let's say, a couple of decades ago. Why the sudden awareness of quantum physics and National Quantum Mission? The idea is to introduce these concepts even early in school, and of course, postgraduate centers in a very big way. Next slide. The reason why it is possible to try to do something about this now is because testing quantum laws in experiments is now relatively easier. It's more possible to test them. The old concepts have been well tested. We have a reasonable theory, so it is good to propagate that theory. Some problems have been identified where quantum computation is exponentially faster than classical computation. So for instance, the search algorithm, data search. In some of these search algorithms, if you use a quantum computing technique, you should be able to finish your job exponentially faster. There is a big speed up compared to classical computation. Like that, there are some classes of problems which involve large databases where quantum physics could be extremely useful. Then there is a lot of application to technology and innovations. Companies like Google, IBM, etc. are also carrying out quantum computing in a big way. They seem to be increasing the number of quantum bits by the day. Job opportunities in industries, therefore, it is believed, will also increase. That is why this extreme interest in quantum physics the world over. Next slide. So the key points, I think Professor Natarajan has summarized it, but I want to make one statement. Originally, it was thought that quantum physics was needed to explain the behavior of very small objects. The problems were seen when you study atoms, molecules, and things like that. But actually, quantum effects play a big role outside the middle dimensions in which we live. If you look at astrophysics, if you look at large galaxies, quantum physics plays a very important role. So the first thing you should understand, it is It was previously thought that only for microscopic objects quantum physics, quantum effects will be seen. That is not true. Large-scale quantum fluctuations are seen. Galaxies, black holes, neutron stars, all of them require quantum physics. Quantum effects are very visible. So in very large bodies and in very small bodies, quantum physics seems to be important. Then why did it take us so long to understand it? Because we live in what is called the world of middle dimensions. If you look at our sizes, what lengths can we understand based on our common sense? Many kilometers, maybe a micron, the size of one human strand of hair. But what will you do if it is smaller than that or larger than so many kilometers? Similarly for time, similarly for mass. So this is the world of middle dimensions. Nature has created us in the world of middle dimensions. Anything outside the middle dimensions, our common sense will not be enough to understand it. Therefore, we have to resort to mathematics. Because in mathematics, you will know the truth. You start with one step. You keep doing some maths. You will know what approximation you used when. So you will know exactly what is happening. So unlike your common sense, mathematics won't tell lies. So in order to understand quantum mechanics, you need to understand not that you can do classical physics without mathematics. Starting from Newton's laws, force balance equations, everything is mathematics. Quantum physics needs a big body of maths. Only based on that, you make predictions. This body of mathematics would include linear vectors, spaces, matrix algebra, differential equations. But we are told, school level, this has to be taught. What is the student supposed to do? Learn all that and come and then start things at school level? It's not possible. No? So you must introduce quantum physics in a pedagogical fashion first. The experiments, again, you can't perform it in every school. So it should be done with minimum usage of mathematics. But in the process, it should not be erroneous. You should not get back with some concepts which are wrong. So although there are many YouTube videos released on all sorts of things in quantum, I find that many of those videos can also give you information which is not quite precise. So adarlam padicha, then there is a problem. You have to be very careful what videos you choose. There are some excellent videos. So one has to identify those and do it. Classical physics is a good approximation to quantum physics in many cases. That is why science could survive all these years with just classical physics. But the world is quantum. Most of the time classical physics will do because we are looking at the world of middle dimensions. That is all. Next slide. So wave-particle duality, for instance, which Professor Natarajan spoke about, I just want to mention this as an aside. This gentleman here, this is the picture of Shinichiro Tomonaga. Tomonaga was one of the biggest pioneers of quantum physics. Japanese person. In those days, this wave-particle duality had to be, introduced, right? Sometimes a particle is a particle, sometimes it's a wave, and so on. So he wrote a drama for the Japanese people even in those days. The quantized electromagnetic wave gives you photons. Photons are corpuscles of light. So he created this lady in his mind. Her name is Miss Photon. So Miss Photon in the drama is supposed to be a big-time thief. She has stolen all sorts of things from all sorts of people and she is very elusive. It is very difficult to get her. Finally, the police go and trap her inside a house which has many windows and doors. Then they say, she's sitting there. So then they talk, how do we catch her? So this is Miss Photon. If you open a window, she will jump out of that window. But they don't know which window. Maybe she will dodge you. Maybe she will jump out of the window, but that policeman may not be able to catch her. So they said, "Number ushara irupom. Let us open all the windows and all the doors. She will come out of one window or door. We will catch her there." They opened all the windows and all the doors. Miss Photon escaped from all the windows and all the doors. See, it's an electromagnetic wave. Light flows out from everywhere. This one, even Japanese people who didn't know any physics enjoyed this play. And I'm told that it was a big hit in Japan. And as you know, light itself has, been very, very important. The International Year of Light was a UN observation for increasing awareness of the achievement of light. Next slide. The photoelectric effect, the mass energy equivalence, and Einstein got the Nobel Prize 1921 given in 22. He was a poet, a pianist, a violinist. The wave particle duality, photoelectric effect, and all these things have been extremely important concepts. Next slide. There was a stamp that was released, Albert Einstein stamp in 1966 for his pioneering work, and this was the Nobel citation. Contributions to theoretical physics, especially for the discovery of the law of photoelectric effect. Next slide. Not just photons. You know that matter has both particles and waves. You want to describe interference phenomena, you use wave-like nature. Atoms transition from one level to another level, you say photons are released. So energy is quantized. Atoms is nucleus surrounded by electrons. The atom is electrically neutral. Then comes the big thing. How do the electrons move around the nucleus? Orbitals. Mr. Linus Pauling must have been a very mischievous person. He introduced this concept of orbitals, got himself the Nobel Prize, explained a lot of chemistry, and put a lot of students into trouble. For the following reason, play that video on atomic orbitals. You see this video. First, see the video. I've taken this video from YouTube. This is the atomic orbital. I'll explain this. Can you just stop that video? Just stop that video. That's enough for me in that video. You see, in the books you will see, column madri, like he showed first, some lines are drawn. But things don't move in a trajectory, in a definite trajectory. In classical physics, there is definite paths. But here that is not true. So what is this dense things? It is the probability of seeing the electron at that space point at that instant of time. So the more the probability, the denser it is. The less the probability, the rarer it is. So even to understand how electrons move around an atom, that old column kind of thing, it's not right. It is wrong. Because it gives you some fallacious ideas that the atom is going like this, then like that, then like, no, it is doing this. So there is a fuzziness in its trajectory. You can only talk of probability of the electron around the atom located here at this time. That is all. So that is an orbital. And that is right. That picture is right. So quantum mechanics is inherently probabilistic. But to describe this probability, obviously it depends upon the qualities of that electron. How do you describe the qualities of that electron? Now I go back to the slides. Next slide. No, you're going back. So no definite paths or trajectories, fuzzy movements. As I said, in classical physics, there is no problem. If there is no error in initial prescription of position and momentum, the future path is completely determined. Whereas in quantum laws, there is a problem. It's inherently probabilistic. To describe this probabilistic nature, for each particle, you associate this wave function, which is supposed to explain the state of that particle. This wave function is going to be a function of, put a bracket there, is going to be a function of x, y, z and time. It obeys the Schrodinger equation. The wave function can be a complex function of space and time. So what is probability? The modulus square of the wave function is the probability density of it being localized around some value y and z at some time t. It can be normalized such that the total probability of having the particle is 1. After all, the maximum value of any probability can only be 1. So you talk of normalizing a wave function, which is a complex function of x, y, z and t. That is the wave function. If it's a one-dimensional motion, it's a function of x and t. If you're not interested in time, if you're only interested in its position, it's a function of x or xyz, depending on the dimension. The physical connection is the modulus squared of that wave function will tell you around the neighborhood of a certain x, y, z and t, what is the probability density. The total probability should be 1 because it has to be somewhere. You can't wish it away. Okay, next. This is the picture which many of you would have seen. This was the Solvay conference. It is considered to be the most intelligent photo in this world. 29 people who attended the Solvay conference, 17 of them got the Nobel Prize because it is the year of women, whatever. That is Madame Curie out there. She had 2 Nobel Prizes. Okay, so this probability business is what got Einstein and Bohr into an argument. And Bohr says, do not tell God what to do. And Einstein says, God plays dice. There is a probability in the whole thing. Okay, proceed to the next slide. Things are much worse than we thought. The act of measurement and the uncertainty principle. What is this act of measurement? Since energy levels are quantized, let us look at 2-level atoms or 3-level atoms. Just 3 levels with definite energy. Now you can say, are there such atoms? Yes. Rubidium, cesium. 3 levels are very close to each other. The other levels are far away. Therefore, I provide enough energy for these 3-level atomic transitions to have the maximum probability. So, such atoms are very useful in experiments and very interesting electromagnetic phenomena have been seen using such atoms. So, suppose I consider a 2-level atom. There are 2 energy eigenstates. Each state has a wave function. So there are 2 wave functions. There are 2 corresponding energy eigenvalues. If it's an n-level atom, there are n states and there are n values of energy. Next slide. Energy spectrum can be unequally spaced, can be equally spaced. You see, if the energy if the levels are very close to each other, that is like classical physics, where if you oscillate a pendulum, it can take all possible values. No? So then you hit the classical limit. I don't think I want to get into degeneracy here. So the state is given by this wave function. Next slide. So where are the properties of this electron or whatever you're studying? Is it in X, Y, Z, and T? No. The properties are encoded in that psi, in that wave function. For instance, I'm here. My properties are encoded in me, not in where I stand, where, at what time of the day, and so on and so forth. So my state should be described by the wave function psi, which I am not interested in her position. I am not interested in the time at which he does something. I am interested in that system. Then I need to just consider the state. So you must understand that there are two ways of looking at things. As a function of X, Y, Z, and T, I'm not interested in that. Then just look at the state. So I must distinguish between the two of them. The state is represented by this bracket. This is a state. Its name is 5 sub 1. And this is another state. Its name is 5 sub 2. Why 1 and 2? I'm looking at a 2-level atom. That's all. But since the energies of these states are definite, I can think of superpositions. And that's where this measurement business comes. Before measuring in quantum physics, you don't know which energy level that 2-level atom was occupying. Maybe it was in state phi 1 with energy E1. Maybe it was in state phi 2 with energy E2. Maybe it was in some combination. I don't know. All I know is when I measured, it was in state phi 1, or rather I measured energy E1, and therefore I know that the associated state is phi 1. The unfortunate thing is, once you do the experiment once, and let us say the outcome is E1, you go on repeating that experiment, you're going to see the same E1. So quantum experiments are done using ensembles of identical atoms. You take 100 atoms, do one trial on each atom. That trial can give you E1 or E2. Go to the next atom. Do it. 100 trials, 100 answers. Now, get to the next slide. Okay. So go to the previous slide. So before measurement, it was in some superposition of phi 1 and phi 2. Let us say the state is psi. So it is some A times phi 1 plus B times phi 2, where A and B need not be real numbers. They could be complex numbers. This is like you're, in a plane, you have unit vectors I and j. You can have 5i plus 4j, that is a vector. But 5 and 4 are already known to you. I don't know what A and B are. If I measure, it will collapse to one of these states, either phi 1 or phi 2. Modulus of A squared is the probability that it's going to be in state phi 1 after measurement. And modulus of B squared is the probability that it will collapse to the state phi 2. Now get to the next slide. So the meaning of A and B is also different from classical physics. This is the probabilistic interpretation. The first, as I said, the first time measurement, suppose the outcome is E1, it's going to be E1 all the time. In 100 measurements, suppose 30 trials give me E1 and in 70 trials I get E2. Remember, there are 100 particles. So 30 of them gave me an outcome energy E1 and 70 gave me E2. The probability of the state collapsing to phi 1 is 3 by 10, 30 by 100. And that of phi 2 is 7 by 10. So that is the connection. Next slide. Since there is no other outcome possible, either it will collapse to phi 1 or phi 2. So modulus of A squared and modulus of B squared are the probabilities of being in phi 1 or phi 2. Total probability can only be 1. Therefore, this is a condition which holds, and the state is said to be normalized. Like you have I dot I is 1 and j dot j is 1 and I dot j is 0, this phi 1 and phi 2, phi 1 is normalized to 1, phi 2 is normalized to 1. That psi, which was a superposition of phi 1 and phi 2, is normalized to 1. And phi1 and phi2 are orthogonal to each other. They are two different states, I dot j 0. That's all. Spelling wrong. Also, since the two states are different, I dot j 0 means phi1 and phi2 are not only normalized to 1, but are orthogonal. What was the state of the atom before measurement? No idea. I don't know. Next one. So this is the famous Schrodinger cat thing, which most of you might have seen. So I'll go through it very fast. Before measurement means open the box. There is a cat inside the box, maybe with some poison or some radioactive material. So the general state is A times the dead state of the cat plus B times the live state of the cat. You open the box. You know whether it is dead or alive. So it has collapsed to one of these two states. This is a quantum superposition. Now there are many quantum numbers, How much time do I have?
10 minutes.
Now, very nice. There are many quantum numbers, It's not just energy, There are many quantum numbers. Electric charge is a quantum number. The electron has charge -1 in units of E. Proton +1 in units of E. You can't change that. That is an intrinsic property of the electron. Like that, there is this quantity called spin. See, there is something very wicked about physicists and the kind of language they introduce. We've had many students tell us spin is this. It is not that. It is not what the bowler does in the cricket stadium. No. Because if spin is just going around, I can go around and change the spin. I can do something in space and change the spin. But I can't. Like you can't change the charge of the electron, you can't change the spin of the electron, period. So it's called an intrinsic or internal quantum number. So the spin of the electron is half. In units of the Planck's constant, h bar is h by 2 pi. So half h cross is the spin of the electron. The electron is defined not just by its charge, not just by its rest mass, 0.51 electron volts, a million electron volts in units of energy, but also by other quantum numbers like spin. So what is quantum about it? Quantum is the electron has spin half h cross. You cannot change it by spinning it around. You can change its orbital angular momentum, not spin. Spin is not r cross p or anything like that. Spin is like charge. So this information about spin is already encoded in that state, that abstract state, ket psi that I wrote. If the spin is half, it is a vector in some internal space, not in this space. It has three components, Sx, Sy and Sz. Now where is the quantum? If you make a measurement on the spin of the electron, the third component of spin, what is this third component? People keep saying Sz, Sz, Sz. What is Z? From where did Z come? When you're making a measurement, to make the measurement, you need to use some probe. The probe is the magnetic field. The magnetic field vector defines your Z direction. The Z direction is defined in the laboratory. So you give a magnetic field and look at the spin of the electron. The Z component will either be along the direction of the field or against the direction of the field. You say Sz is plus half h cross or minus half h cross. So there are two values of Sz that are available. That is after measurement. Otherwise, it is in a superposition of these two Sz states. To make matters worse, I cannot measure Sx, Sy and Sz simultaneously to arbitrary precision. There is a problem there. And to understand that, one has to worry about matrix mechanics, the commutator operation, linear vector spaces, so on and so forth. So without the mathematics, if this has to be taught, it has to be taught more or less at the level that I'm talking now, where you draw analogies with unit vectors I and j if you wish. Just see to it that what you say is correct and doesn't lead to confuse, concepts in the mind of the students. I think that is important. Next slide, please. So I did speak about all these things, I think. So Sz has values plus half H cross and minus half H cross. It's true of the proton and the neutron and all that. So you want to define the state. Right? That state is defined by the rest mass, the electric charge, the spin, the Sz value. There are many other quantum numbers. There is color, there is flavor, there is charm, there is beauty. They're all names of quantum numbers, by the way. So you have to tell all that. And two objects are different if at least one quantum number is different between the two objects. Next slide. So what are these qubits? Now we get to how does this translate to technology? You first define something called a qubit or a quantum bit. Now a quantum bit, I have two levels. Spin maybe plus half H cross and minus half H cross. They don't overlap. So they are two states. Like 0 and 1, like a classical bit, but with one difference. They are in a superposition. Right? So you can superpose things. Superposition is at the heart of quantum technologies. Not just superposition, entanglement. These are two resources that you really need for quantum technologies. So I have said all this. I have said this too. Similarly, like I can Sx, Sy, and Z simultaneously, I cannot measure position and the momentum corresponding to the x coordinate simultaneously to arbitrary precision. You have to understand what this means. Nobody says you cannot set up an experiment to measure x and p sub x simultaneously. Nobody says you cannot make an experiment to measure Sx, Sy, and Sx simultaneously. Please do it. If you do it simultaneously, I'm giving you the uncertainty principle in its simplest form. If you measure simultaneously, you can't measure both of them to arbitrarily accurate precision. That is all that it means. You can measure many things simultaneously to arbitrary precision. You can measure x and p sub y to arbitrary precision. You can't measure x and p sub x to arbitrary precision. The word simultaneously is very important here. Okay? So there is a spread in the measurement. Don't think that it is because of the least count of the apparatus. You give me an apparatus which is fantastic. It has nothing to do with the least count of the apparatus. Because of this probabilistic, internally there is a probabilistic thing here. Therefore, you cannot measure it simultaneously. Not because your apparatus is rickety. So the spread in x and the spread in px is supposed to be greater than or equal to h cross by 2. This is the simplest version of the uncertainty principle. We normally trace this to Heisenberg, but there are better versions given by Schrodinger and all. So is there an example of a minimum uncertainty state? Yes. Laser light. This is a minimum uncertainty state. Except that x and px are the electric. Remember, light is electromagnetic waves. It's not position and momentum. X and px are like the electric and magnetic field strengths. But this is an example. Delta x, delta px is equal to h cross by 2. Similarly, if you look at the ground state of the quantum simple harmonic oscillator, delta x and px, if I put all parameters to unity, it will have value 1 by root 2 each of them. And that's a minimum uncertainty state. Next slide. There are systems where delta px is less than 1 by root 2 and delta x is greater than 1 by root 2. Then it is said to be squeezed in momentum. Otherwise, it is squeezed in position. There is something called squeezed light, that is very useful for gravity waves. Because when you squeeze, what do you mean? The spread is becoming less and less. So you can probe better. The least count is smaller and smaller. Therefore, gravity waves are very weak signals. I will use light to probe gravity waves. It's something like this, Once you squeeze in x, in p it has to dilate. Look at this fellow. We squeezed in x, don't dilate. So it's something like that. Next slide. So that is squeeze light, and I think I should be winding up soon. So get going to the next slide. Aha, go up. Go to the earlier slide. Yes. So I can superpose, spin up with, now I want to do something more. I want to do a complicated superposition and then stop the stock. Spin up of the first particle, first electron with spin down of the second electron plus spin down of the first electron with spin up of the second electron. You see, in cases like this, in this kind of complicated two-system or multi-system situations, the two states are entangled. This is called quantum entanglement. And because of this, if I make a measurement on the first system, I can get information on the second system. So entanglement is a big resource in quantum technologies. There are several good videos, and these electrons can be separated by any spatial distance. They were born entangled. Several good videos. I want to show one video and stop the talk. I didn't use the blackboard. I just wanted it as an alternative. I'm a theoretical physicist. I feel nervous if I don't have a blackboard. So, or a whiteboard for that matter.
Seem to violate our understanding of space and time. But what is entanglement really? These two coins are not entangled. If we flip this coin, it won't have any effect on the other. Each coin, when flipped, will have a 50% chance of landing heads or tails, and that's true no matter what you see when you look at the other. But what if we could use some magic trick to entangle these coins? The one comes up heads, the other will come up tails, no matter how fast they are. Let's say I give this coin to Alice and this one to Rob, just before they fell on rocket chips going in opposite directions. Alice and Rob are each under strict instructions not to flip their coins until they've been traveling for 10 years. When the time is up, they each flip their coin and immediately send radio signals to each other with the answers. But while those signals might take years to reach their destinations, means that the moment Alice sees heads, she knows that Bob's coin landed tails, and vice versa. Alice doesn't have to wait for Bob's radio signal to arrive to know what it will say. Alice's coin had a 50-50 chance of coming heads, unless it does, Bob's coin is tails 100% of the time. Because Bob's signal is still traveling to her when she finds out the answer, it's as if Alice has predicted the future. This might sound impossible, but it's exactly what quantum entanglement does to individual particles in experiments. Let's say you carefully prepare two particles in a lab to make them entangled. One way to set this up is to ensure that they will have opposite spins, meaning they'll line up opposite to each other in a magnetic field. Then, you separate the particles by thousands of miles and measure the spin of both of them. If you find that its spin points up, the others will always point down. Like in the coin example, whenever Alice measures the spin of her particle, if it has spin up, she'll instantly know that Bob's particle has spin down, or vice versa, no matter how far away they are.
Stop it. That's all I want. I want to draw attention to the fact that there are very many videos on entanglement. Many of them can give you very confused ideas and wrong ideas. In general, if you want to see something on quantum physics, I would suggest anything put up by Perimeter Institute. You can trust them and you can go ahead and take a look at them. So, I conclude with this. So, in a pedagogical manner, see, I have made statements. Delta x, delta p greater than or equal to something, then something else. See, all this, you derive it with mathematics. But if you want to introduce this in a pedagogical manner, at least it should not be wrong or ambiguous or confusing. So when you introduce quantum concepts to schools and undergraduate colleges, the main aspects to be introduced are quantum numbers, wave function against the state, this difference, measurement, ensembles, uncertainty principle, qubits. Give examples of qubits. No, the next slide, please. Superposition and entanglement. These two are very important for technologies. So there are videos available for popularizing these, but beware of many videos that provide wrong or ambiguous physics. Mathematics is absolutely essential for proving many of these concepts because they cannot be understood using classical laws. Classical physics needs mathematics. Classical physics has classical probability theory. Please don't think that probability theory has to do with quantum mechanics, no. Classical physics also uses maths, Newton's equations, and so on. This is a different style of intuition which human beings do not have. So I want to stop here. Thank you.
The floor is open for discussion. You can clarify your doubts.
If you have any questions, and maybe you have lots of questions.
Good morning, ma'am. Thanks for your nice talk. So I have a basic doubts. So you have told that the entanglement is possible only two atoms, or it is a many atoms is possible.
Many atoms. You need at least two. You need two different systems for entanglement. Could be two photons, two electrons, an electron and a photon, doesn't matter. It can be three, it can be four, it can be many things. In bulk materials, there is entanglement. Multipartite entanglement goes by the same principle. Things don't have to be close to each other. They were created entangled and they could be very far away. But if they are entangled, doing an experiment on one of them is going to tell you information about many of them. Yeah.
One more thing, ma'am. So the measurement collapse the state.
Yes.
When but in quantum computing, so information never be lost.
It depends because the information can be transferred. Take for instance a two-level atom which is doing atomic transitions. How does it go from one state to another state? You shine light on it. You can work with laser light. So the atom interacts with laser light and it moves either up or down, releasing photons or absorbing photons. So part of the information has gotten transferred also to the light. So normally when we look for quantifiers of information, you could either work with the atomic qubits, those two levels, and define things like the extent of entanglement, the kind of information and so on, or you could look at the light and you look at things like the von Neumann entropy, subsystem von Neumann entropy, the entanglement and what it contains and so on. So an information transfer will happen. The net information will be there, but between the two objects that are interacting, there could be interaction. There will be, in fact, information transfer most of the time.
Once it's measured, so the state will be changed.
The state will be changed. It will fall into one of its states.
Then how do you relate with the source?
How do I what?
If the state is changed, means the information is changed. But we can measure
Changed to what? The atom changed its state from the upper level to the lower level. Did it not release a photon in the process? Did not that photon get detected in the laboratory? Was there not a photocurrent which got detected in the laboratory? The information is there. The atom released a photon. That photon was absorbed by the light, the laser light. So there is an information transfer. But how do I know that that has happened? I know that there is an atomic transition. That is how I know it. You can ask your question in Tamil also. That's okay. Oh, Nirmal, hello.
I have a naive question. Many may know this, but when we talk about quantum entanglement of two or more particles, I'm just wondering if we can think of stimulated emission, which doesn't occur naturally, right? We have to do engineer material, tailor materials. So I believe this is also done via extraordinary effort of entangling, or can we expect nature to have these particles getting entangled, disentangled, without us noticing it, or should we engineer them to?
You don't have to engineer them. It gets entangled and disentangled. Like the analog is the energy-time uncertainty relation. Your least counts are too large for you to observe it. Virtually, you see this entire virtual fluctuation business, this is going on. Things are being produced, things are being released. They're all interacting with each other, complex states. Your least counts are to watch. The experimenter is the man to be pitied. Because if he says, I don't see this effect, I will say, make a better apparatus. The theory will tell you, it is going on. These processes are going on, what we call virtual processes. But you have to engineer if you want it for technologies. You can't even detect the entanglement, what are you going to do with it? So you engineer it. And carefully, so that you get the correct entanglement that you wish, so that you can use it. And you should trace the error. If the entanglement diminishes, you should be able to boost it up. You have to do things like that.
Where do you see this entanglement in nature? All over, all the quantum fluctuations you talk about, all these?
Essentially, most states are entangled states. See, there are always correlations, right? It's like saying, in a different context, which you will understand, where do you see chaos? Most states are chaotic. But seeing it, quantifying it, harnessing it for technologies, that is the problem. Now the question is how much entanglement? A Bell state is maximally entangled, but many states are minimally entangled, little bit less entangled. You can make a certain class of measurements which just doesn't entangle. Those are to be tailored actually. Yeah. But you need two objects or more. Yeah.
Morning, ma'am. I'm person of chemistry. I have few doubt on superposition state. Actually, solving Schrodinger equation gives proper eigenstates. Then the superposition state is just introduced as adapted.
No. Eigenstates are like your unit vectors I and j. They are the basis states. But 5i plus 4j uses both unit vector I and unit vector j. So there are two basis states I and j, unit vector I and j, and the general vector is a combination 5i plus 4j. Like that, the energy eigenstates are eigenstates. They are called the basis states. They are analogous to your ij, ijk, and so on. A state is a superposition of all these eigenstates. The first eigenstate with some probability amplitude, plus the second eigenstate with some probability amplitude, and so on. It is not ad hoc. Because of the superposition, how do I know that it is superposed? As I said, the coefficient that comes before each basis state, when you mod square it, it should agree with the probability that it has collapsed to that state after doing the measurement. Look at the two-level atom. There were two levels, E1 and E2, with wave functions phi1 and phi2, basis states, phi1 and phi2. I said, in the example that I considered, 100 trials were done. 30 times it fell into E1. 70 times into E2, which means the probability of collapsing to the state with energy E1 is 30 by 100. And the other one is 70 by 100. That is an experimentally measurable thing. So this superposition translates into probabilities. The superposition coefficients when mod squared give me the probabilities. So there is nothing ad hoc about it. It's experimentally verified. That's what I'm saying.
Superposition state have different energy. Suppose
It's not an energy eigenstate. It is not an energy eigenstate. The basis states are energy eigenstates. The superposed state is not an energy eigenstate. You can talk of the average value of energy in that state. It's the expectation value. I can say, so 30 trials E1, 70 times E2, take the average. It's not an eigenstate. An energy eigenstate has definite energy. The superposition need not have that energy. You don't have it. So that's it, right? Yeah. Okay. I think we Thank you.
At the outset, I express my sincere gratitude to our respected resource person, Professor Lakshmi Bala, for her enlightening and thought-provoking lecture on quantum concepts. Ma'am, your ability to present complex ideas with such clarity and insight truly enriched our understanding and inspired everyone present here. Thank you so much, ma'am, for your precious time and valuable contribution to this program.